right, guys, welcome back. We're going to start right here with this function. Take a look at it. And let's say that you stand on the right-hand side of this function and you shrink yourself down to the size of an ant. Here's you, ant size. And you're standing on the right side of this function, on the function, and you run on the function towards the x value of 3. The question I'm asking right now is, what y value are you approaching when you approach an x value of 3? Just visually looking at it, as my little ant size me gets closer and closer to an x value of 3, I am getting closer and closer to a y value of 4. Let's do the same thing on the other side. Shrink down to ant size. Here's you, ant size. And you are going to run on this function towards, again, the x value of 3. What y value is ant size you getting close to when you get close to an x value of 3? The y value that you're approaching is a y value of 4. And this concept of what y value are you approaching is called a limit. In math, a limit tells you what y value a function is approaching as the x value approaches a certain number. In other words, a limit is a y value approach. Again, the question is, what y value are we getting close to as we get close to a certain x value? And the key word here, what you need to remember, is that a limit is a y value approach. A limit can come from the right side or from the left side. And the way we write all this down is like this. We say the limit of the function as x approaches the value of 3. Now, if we're coming from the right side, we put a little plus sign indicating positive values or values on the positive side. And so in this case, for this problem, we've said the limit of the function as x approaches 3 from the right side is 4, because the limit is the y value approach. When you're asked for the limit, you're telling the y value that you're approaching. Now, if we came from the other side, we would write it as the limit of the function as x approaches a value of 3 from the left side, meaning the negative values. And again, in this case, our limit was 4. The y value we were approaching is 4. Like I said, limits can be side-specific, meaning they can come from the right or they come from the left, but they don't have to be. If a limit doesn't specify a side, if it just says the limit of the function as x approaches 3, then that means you actually have to approach from both sides. You have to do both the right and the left. And if those values match, if your answer from the right and if your answer from the left matches, then that is the answer for the overall limit. And if they don't match, then we say the limit does not exist.
If Miss Heron can answer this problem correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh God, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Our new state champions, the North Shore Mathletes.
And I'll talk about that notation in just a bit. Let's look at another problem here. Let me have you quick sketch f of x equals x minus 2 squared plus 1. I'm going to go over 2, up 1, put a point there, and then it's parabolic. So now the question is, what is the limit of the function as x approaches 2 from the right-hand side? Here's our x value of 2. And so we're going to put ourselves on the right-hand side of 2, anywhere on the right-hand side of 2. Shrink down to an ant-sized version of yourself and jump up onto the function. There I am. And I'm going to run towards the x value of 2. And as I get to the x value of 2, what y value am I approaching right there? The y value is 1. And so the limit of the function as x approaches 2 from the right is 1. Different question now. What is the limit of the function as x approaches 2 from the left. So I'm going to put myself on the left-hand side of the function. I'm going to shrink down to ant size, and I'm going to jump up onto the function anywhere on the left-hand side of the function, on the left-hand side of 2. And now I'm going to run from the left toward the x value of 2, and what y value am I approaching? I am again approaching a y value of 1. So the limit from the right was 1. The limit from the left was 1. So it's fair to say that the limit of the function as x approaches 2 is 1. This means that both from the right and from the left, the y value that we approach is 1. Now consider this. Let's pretend that we're back at school and you've made me really mad for some reason, okay? So you come into my classroom and you sit down, and I decide that I want to come over and yell at you because that's exactly my personality. I yell at people a lot, okay? So you come in, you sit down at your desk, and I storm towards you, and I'm going to yell at you because I'm mad. But pretend that I didn't know this, but you have the super special ability to boom, teleport away. All right, so as I'm storming towards you to yell at you, you just, boom, you teleport out of there, and you're not there anymore. It's just an empty chair. Now, what was my plan? My plan was to come over and yell at you. All right, I was approaching you. I was coming towards you. The fact that you, poof, disappear the moment I get there, that doesn't change the fact that I was approaching you. And it's the same with limits. A function doesn't actually need to exist at a certain point in order for the limit to exist. Look at this function here. The question is, what is the limit of the function as x approaches 4 from the right? So we find the right-hand side, we shrink ourselves down to ant size, we jump up on the function anywhere on the right-hand side of 4, and we run from the right towards the x value of 4. What y value are we approaching as we get to an x value of 4? We are approaching the y value of 2. But if you look closely at the function, there's a removable discontinuity there. The function doesn't actually exist at 4. But that doesn't matter. We are approaching a y value of 2. Whether or not that value exists when we get there is not our concern. The fact is we're approaching that value. So now let's go again. The limit of the function as x approaches 4 from the left. Find the left-hand side. Don't mix up your right and your left. Shrink yourself down to ant size. Jump onto the function anywhere on the left-hand side of 4 and run towards 4 from the left-hand side. What y value are we approaching as we get close to 4 from the left-hand side? We are again approaching a y value of 2. So we can say that the limit of the function as x approaches 4 is 2. But what is the actual value of the function at 4? F of 4 does not exist in this problem, and there are two different ways that you can write does not exist. A really common way is to just write DNE, does not exist, or you can use the symbol for there exists, it's like a backwards E, and then slash through it. That means there does not exist. Does not exist is not the same as undefined. Undefined implies that there's a vertical asymptote, and I guess you could write no solution, but when we're dealing with limits, the more common vernacular is does not exist. Now let's consider another function. Let's look at a specific function, f of x equals 1/2 x plus 1. We're able to sketch this pretty easily. It's just a line. We're going to go up 1, and then from here we're going to go up 1, over 2, put a point there, and we can draw in our line. And now let's say that we're asked, what is the limit of this function as x approaches 2? I'm not specifying from the right or from the left. I just want to know as x approaches 2. Well, if I'm accurate with my graph and I've done a good job, I should be able to see an x value of 2 there. And because this is a very straightforward function, it's not hard to figure out these values. And I can say, well, I'm being asked for the limit as x approaches 2. That means I have to come from the right-hand side. So I'm going to shrink down to the size of an ant, and I'm going to run towards the x value of 2, and I see that I have a y value of 2. I also have to approach from the left side, and I'm going to shrink down to the size of an ant, and I'm going to run towards my x value of 2, and again, I have a y value of 2 because the approach from the right and the approach from the left both equal the y value of 2. I can say that the limit of the function as x approaches 2 is simply 2. Sometimes, though, they don't have a graph-based limit question. Sometimes it's a little more abstract. Sometimes they want you looking at values instead of a picture, like this. This same problem presented as a table of values looks like this. The question remains the same, the limit of the function as x approaches 2, and we go from the right and from the left, and we see if the values match. So here's 2. Here's the x value of 2. And values to the right of 2 would be numbers that are bigger than 2. Not just visually which side is the right-hand side, but numerically which numbers would fall on the right-hand side. Those would be numbers that are larger than 2. And if we look at these numbers that are bigger than 2, and we approach the x value of 2 from the right-hand side, look at what's happening with the y values. We are getting closer and closer and closer to a certain y value. Let's go again from the left-hand side. If we approach the x value of 2 from the left-hand side, looking at our x values, we are getting closer and closer to 2, and then we compare the y values. Our y values are getting closer and closer to a certain value. Now, I didn't actually write that number in. That number exists for this graph, but it doesn't necessarily have to. Again, the value does not have to exist for the limit to exist. It's the approach that matters, and you can see that we are approaching a y value of 2 as we approach from the right and from the left. So the limit of the function as x approaches 2 is 2. Now let's take a look at a few more situations here. Let's look at this function. First question, is this a function? Take a look. Yes, it's a function. It passes the vertical line test. So our next question, what is the limit of the function as x approaches 2 from the right? Get yourself on the right-hand side of 2, shrink down to the size of an ant, run on the function from the right-hand side, approaching the x value of 2. What y value are we approaching? We are approaching a y value of 3. Next question, what is the limit of the function as x approaches 2 from the left? Give it a try. We get on the left-hand side of 2, we shrink down to the size of an ant, we run on the function, and we see that we are approaching a y value of 1. So now, what is the limit of the function as x approaches 2? Because the value from the right and the value from the left do not match, the limit does not exist. And again, you can use this fancy symbol, or you could write DNE for does not exist. Either one is completely fine. Finally, what is the value of the function at 2? What is f of 2? You can look at the pretty picture and you see that f of 2 is 2. Okay, now stick with me here. Watch. Look at the function. I'm going to get rid of that and add in that. This is now a different function. And the first question, is it in fact a function? Yes, it passes the vertical line test. We are just fine. What is, same first question, the limit of the function as x approaches 2 from the right? We get the same answer. It is still 3. Same second question, what's the limit of the function as x approaches 2 from the left? Same answer. It is still 1. Therefore, what's the limit of the function as x approaches 2? It still does not exist, but same question here. What is f of 2? We can look and see that f of 2 is 1. Okay, let's go again. Watch. Look at the function. Now let's go one more time. Is it still a function? Yes, it passes the vertical line test. What is, again, same first question, the limit of the function as x approaches 2 from the right? It's still 3. What's the limit of the function as x approaches 2 from the left? It's still 1. Therefore, what's the limit of the function as x approaches 2? It still does not exist. But now, what is f of 2? If you look at the x value of 2, there is no corresponding y value, so therefore we could say that f of 2 does not exist. Moving on now, let me have you quick sketch y equals 3. There we go. So now let's ask a question. What is the limit of the function as x approaches 1? Let's get a couple x values thrown in here. Here's our x value of 1. If we approach our x value of 1 from the right-hand side, we get a y value of 3. If we approach from the left-hand side, we get a y value of 3. The limit of the function as x approaches 1 is 3. Now, what about the limit of the function as x approaches, say, 4? Here's 1, 2, 3, 4 right here. So let's approach an x value of 4 from the right, and we get a y value of 3. Let's approach from the left. We still get a y value of 3. The limit of the function as x approaches 4 is 3. How about the limit of the function as x approaches 2? Here's 2. And now as we approach 2 from the right, we get a y value of 3. From the left, we get a y value of 3. Again, the limit of the function as x approaches 2 is 3. What do you think we're going to get for the limit of the function as x approaches 0? We're going to get 3. How about the limit of the function as x approaches -5? We're going to get a value of 3. Now this is where it's really important to pause and go all the way back to the beginning. For this very first problem, I didn't tell you what this function was, so using the f of x symbol is all we could do. For this second problem, though, we know that the function is x minus 2 squared plus 1. So for each of these limit notations on the right-hand side, instead of writing f of x, we could have written the actual function, x minus 2 squared plus 1. This problem would have been written as the limit of x minus 2 squared plus 1 as x approaches 2 from the right. Instead of writing f of x, we could have written what the actual function was. Scooting down, I didn't know what this function was, but moving down here, we knew that this function was 1/2 x plus 1. So instead of writing plain old f of x, we could have written the problem as the limit of 1/2 x plus 1 as x approaches 2. You don't have to write f of x. You can write what the function actually is. So coming back down to where we are now, for each of these limits, instead of writing f of x, I could be writing what the limit actually is. And what you'll see is we have the limit of 3 as x approaches 1. That equals 3. We have the limit of 3 as x approaches 4 equals 3. We have the limit of 3 as x approaches 2 equals 3. We have the limit of 3 equals 3. And again, we have the limit of 3 equals 3. It's safe to say that no matter what x value we're approaching, the limit of 3 equals 3. We could have done this exact same process with any y value. This idea can be written as the limit of k as x approaches a equals k, where k is a constant. When a number is not a variable, it's considered a constant. So what we say here is that the limit of a constant is the constant. The limit of a constant as x approaches any value is the constant. And we can shorten that to the limit of a constant is the constant. Say that. The limit of a constant is the constant. The limit of a constant is the constant. That's going to be an incredibly important property for us as we move forward. So what can you tell me about the limit of 15 as x approaches 9? The limit of a constant is the constant. Your answer is 15. What is the limit of 1 as x approaches 0? The limit of a constant is the constant. Your answer is 1. What's the limit of 7 as x approaches 2 from the right? Right, left, it doesn't matter. The limit of a constant is the constant. Now quick sketch f of x equals x. Now I'm going to throw a couple values on here. We've got over 1, up 1. So the new question is, what is the limit of the function? And in this case, the function is x. What's the limit of x as x approaches 1? We find 1. We jump up onto the function, approach 1 from the right-hand side, approach 1 from the left-hand side, and you see that our y value is 1. The limit of x as x approaches 1 is 1. Now let's try 2. What's the limit of x as x approaches 2? Here's 2. Get on the right-hand side of 2, approach 2 from the right. You'll see the y value is 2. Approach 2 from the left. Again, you see that the y value is 2. The limit of x as x approaches 2 is 2. How about the limit of x as x approaches 0? 0 is just the origin. Approach from the right. Approach from the left. You see that the y value we get as we approach from both sides is 0. One more time. What's the limit of x as x approaches negative 2? We find negative 2. We get on the right-hand side, approach negative 2 from the right. You see that our y value is negative 2. Approach from the left. You see that the y value is negative 2. The limit of x as x approaches negative 2 is negative 2. It's pretty clear what's going to happen. What do you think the limit of x as x approaches 5 is? Even without seeing it, I can tell you that it's 5. This property can be written as the limit of x as x approaches any number is the number. The limit of x as x approaches any number is the number. This is referring to the function x, and the limit of x as x approaches any number is always just the number. This is the other property that will be extremely valuable for us as we move forward. So let's see what you're remembering. What is a limit? A limit is a y value approach. What is the limit of a constant? It's the constant. And what is the limit of x as x approaches any number? It's just the number. So let me ask you this. What's the limit of 7 as x goes to 1? What's the limit of x as x goes to 5? What's the limit of 3 as x goes to 1/2? What's the limit of x as x goes to 12? What's the limit of 0 as x approaches 1? And what's the limit of x as x approaches 3/4? The very first one, the limit of 7, is just 7. What's the limit of x as x goes to 5? 5. What's the limit of 3 as x goes to 1/2? It's 3. Then we have 12, we have 0, and we have 3/4. The limit of a constant is the constant. The limit of x as x approaches any number is the number. These two properties are the building blocks for what we need to figure out as we move forward. Beyond those two super important building blocks, there are 6 or 7 different limit properties, but they pretty much boil down to 2 concepts. First, limits can separate at addition, subtraction, multiplication, and division. Before we look at the second property, let's try a problem with this one. We have the limit as x goes to 2 of 4x squared plus 3, and I know that limits can separate at addition, so I'm going to write this as the limit as x goes to 2 of 4x squared plus the limit as x goes to 2 of 3. I also know that limits can separate at multiplication, and 4x squared is nothing more than 4 times x times x. So I'm going to separate each of those limits. I have the limit as x goes to 2 of 4 times the limit as x goes to 2 of x times the limit as x goes to 2 of x plus the limit as x goes to 2 of 3. Now I can evaluate each of those limits. What's the limit of 4 as x goes to 2? It's just 4. What's the limit of x as x goes to 2? It's 2. What's the limit of x as x goes to 2? It's 2. plus, what's the limit of 3 as x goes to 3? It's 3. So we have 4 times 2 times 2, which is 16, plus 3. We end up with 19. The limit of 4x squared plus 3 as x goes to 2 is 19. Now the second important property makes this process a little bit easier for us. The second important property is that constants and exponents can be pulled out of the limit. Let's try the same problem again, but now we can use the second property also. First, we separate the limit at addition. And then we can pull the constant and the exponent out of the limit. It looks like this: 4 times the limit as x goes to 2 of x squared. So the constant and the exponent has been pulled away from the limit of x as x goes to 2. So now evaluating the limit of x as x goes to 2, we know that's just 2. So we have 4 times 2 squared plus 3, which again gives us 19. Try this problem. Using the idea that limits can separate at addition, subtraction, multiplication, and division, and that constants and exponents can be pulled out of the limit, I end up with this. Which then gives me, evaluating the limit of x as x goes to 5, 5 squared minus 4 times 5 plus the limit of 3 as x goes to 5 is just 3. That gives me 25 minus 20 plus 3, which is 8. Try another. Evaluate the limit and see what you can come up with. Using our properties, we can separate the different pieces of this limit to look like this. And evaluating each of these inside limits, the limit of x as x goes to 0 is simply 0. We get 5 times 0 squared plus 3 times 0 to the 4 minus 15 times 0 cubed plus 8 times 0 squared plus 9 times 0 plus 2, and we end up with 2. But you're probably seeing something interesting at this point. Compare this to the original function and the value we're approaching. Looking back at the previous problem, compare this to the function and the x value that we're approaching. What do you see as a shortcut? What could we have done to evaluate these limits? We could have just substituted. To evaluate a limit, the first thing you try is substitution. And if substitution works, then cool. We know that substitution works if we get a number for an answer. If you get a number, then substitution has worked and you're cool. If you don't get a number, you might get something like 0 over 0 or a number over 0. That means substitution didn't work. And we'll get to that on another day. Let's try one more problem before you go. Evaluate the limit. We know that to evaluate a limit, the first thing we do is substitute. And if substitution works, then cool. So I'm going to plug in my 2. On the top, I get 8 times 5 is 40, plus 4, that's 44. On the bottom, I have negative 1, and we end up with negative 44. Negative 44 is a number, substitution has worked, and we're cool. You know what? We need just one more problem. Let's take a look at the limit as x goes to negative 1 of x squared plus x plus 2 over x plus 1. Evaluate the limit. You should have negative 1 squared plus negative 1 plus 2 over negative 1 plus 1. On the top, you get 1 minus 1 plus 2. On the top, you have 2. On the bottom, you get 0. 2 over 0 is undefined, not cool. Substitution did not work, and again, we'll work on that another day. All right, I hope this all made sense. If you have any questions, let me know. Have a great day.